Hi there, folks. Today we are going to talk about eigenvalues and eigenvectors. Now, eigenvalues and eigenvectors, they can be some of the most difficult to understand things, but sometimes folks find it the easiest to understand things. We're going to hopefully explain it in a way where it is the easiest to understand things, but we shall see. Here's just a brief overview of what they're about, though. Eigenvalues and eigenvectors are used to identify and classify equilibrium values in different systems. Positive eigenvalues means the system is unstable, leading to populations exploding in chaotic ways, while negative eigenvalues mean the system is stable, so the populations are going to be approaching some particular value. You can also get complex valued eigenvalues, which would mean that the system is either stable or unstable, but that it's going to fluctuate wildly as it approaches or escapes equilibrium. Eigenvalues are a very major topic when we're talking about dynamics. We can use them to understand how a system is functioning. And before we actually calculate them and determine what they are, let's do a quick overview of what vectors and vector fields are. And so we know that a vector is something which has a direction and a magnitude. That's really the defining characteristic. So you have a direction, you have a magnitude. A vector field, such as something down here, is where we have a large number of vectors all in some coordinate system. Now, the interesting thing is a matrix can be thought of as a way to transform one vector into another vector. That's going to be the big thing. And let's actually go to the whiteboard to show how that would work. And so here we see a 2x2 matrix, and this matrix is being multiplied by a vector, and it gives us a new vector. And so we start with v1, we end with v2. We could put any vector in here, and this matrix is going to transform this vector into some other vector. I think the only one that would stay the same is probably going to be 0, 0, but there might be others. And that's kind of what the idea of the eigenvalue and eigenvector are. If we look at this particular example, with this matrix A, when we multiply by v1, our v2 is a scalar multiple of our v1. These two vectors are going in the exact same direction. And it's easy to see if you were to just graph them out. This one's going to be going 3 over and 5 up. This is going to be going 7 times that amount, but it's still going to be going in the proportion of 3 over and 5 up. And we can even see that here, where we factored the 7 out. And so here we have our matrix A, we have a vector, and it's equal to a scalar multiple of that exact same vector. This is what the eigenvalue and eigenvector are all about. The eigenvector is this vector here. And so the 3, 5 in this case would be our eigenvector. The 7, the scalar, is considered our eigenvalue. Now, as mentioned, depending on what the eigenvalue is, this system could be growing and growing and growing. It could be shrinking and shrinking and shrinking. It could be taking things and making them negative. But we could also get some things where we have complex numbers involved. And that gets a little bit more interesting. For now, let's just focus on the real case. And so we use this notation, the Greek letter xi and the Greek letter lambda, to represent the eigenvector and the eigenvalue. Often when we're talking about the eigenvector, we don't write the vector notation with the little arrow on top if we're using the xi. Xi is pretty much exclusively used for the eigenvector. So if you ever see this symbol, know that we are talking about an eigenvector. Lambda is also going to be used pretty exclusively for the eigenvalue, at least for the time being. Later on, we might use it for other things, but pretty much if you see a lambda, we're talking about an eigenvalue. And so now the big question is, how do we actually find them? And that can be a little bit tricky. And so let's see if we can figure it out. Oh, and here's what we just showed. Here's the formal definition of an eigenvalue and eigenvector, by the by. It's when you have a matrix A, if you can find a vector xi such that when you multiply A times c, you get a scalar multiple of c. Then the scalar, lambda, is the eigenvalue, and the vector, c, is the eigenvector. In order to find them, you might just try and solve this equation, because it is just an equation, right? It's A times c equals lambda times c. And so if we were thinking with our algebra 1 hats on, we might just bring them over, factor, and get that lambda is equal to A or c is equal to 0. Well, there's a problem with that. And the main problem with that is these are not numbers. A corresponds to a matrix. C corresponds to a vector. And so this approach is not going to work. And so let's see if we can find some different way to solve this equation. And so A times c equals lambda times c. And so the algebra 1 idea is relatively good, but it's missing the idea of matrices. And so let's start by moving everything over to one side. That'll give us A times c minus lambda times c equals 0. Where remember, this is a vector, and this is a matrix. Now, if this lambda were a matrix, we could factor the c out, but it's not. The good news is we have a way of making it a matrix, and that is by using the identity matrix. Remember that the identity matrix, I, is equal to 1 with a whole bunch of zeros everywhere else. If we're talking about 2 dimensions, it looks like this. If we're talking about 3 dimensions, well, it'll look like this. We know that when we multiply this by anything, we're just going to get that same thing out of it. And so if we were to put an I in here, make this A times c minus lambda times I times c. Well, I times c is just going to give you c. And if you want, we could just take a look at this. 1, 0, 0, 1 times 2, 3, or whatever vector we're dealing with. It's going to be 2. It's going to be 3. And so we know that this is still true. We also know that we have some of the properties of matrices. And so we could do the I times the c, or we could do the lambda times the I. Well, if we're doing a number times I, such as, let's say, the number 3 times 1, 0, 0, 1, that is going to give us a matrix with this number on the main diagonal. But now this is a matrix, and this is a matrix, which means we can factor this c out and be left with this A minus lambda I. So it's A minus lambda I times c equals 0. Now, ideally, we don't want this c to be the 0 vector, because 0 vector doesn't have a direction, and the entire point of this is to find a vector which has the same direction when you apply the matrix to it. And so now we just have to figure out when we can multiply this matrix by some vector and get 0 out of it. And depending on what this matrix is, when you do A minus lambda I, you could get different values for this c. Let's do one example real quick to show that we can multiply a matrix times a vector and actually get 0. Let's say that we have 2, -5, and then let's say that we have 6, or how about a -6, and then let's make this be a +15. If we wanted to find some vector to multiply this by to give us 0, 0, well, if we look at the first row, we would need to have something like a 5 and a 2. Because 2 times 5 is 10. 5 times 2 is 10. And it was a negative. So this would give us 10 minus 10, which is 0. On the bottom, negative 6 times 5 is negative 30. 15 and 2 is positive 30. And we get 0. And so it is now possible to find a vector such that this matrix times this vector gives us a 0 vector. Note, this would be a 0 vector in this case. And so what makes it so that this thing is so special? What is so special about this matrix that makes it so that we can multiply and get this 0? And it turns out it all has to do with the determinant. If we look at this matrix and we wanted to find the determinant of 2, negative 5, negative 6, 15, well, 2 times 15 is 30, minus 30 gives us 0. If we ever have the case where the determinant of this matrix is equal to 0, then it is possible to find some combination like this, some combination of matrix and vector where they multiply together and give you a 0. In linear algebra, this is called linear dependence. The idea that this second row and this first row are really just scalar multiples of one another. Our goal is to find a matrix which has a determinant equal to 0. And we can do that. Looking at this, if we set the determinant of A minus lambda I equal to 0, then we can solve for this eigenvalue. And once we find the eigenvalue, we can plug it in and figure out what the eigenvector is. Let's try that sample problem that we started out with and see if we can figure that one out. So that was the matrix 2, 3, 5, 4, I believe. And so let's say that we are given the matrix 2, 3, 5, 4. We are asked to find the eigenvalues and eigenvectors. Let's see if we can do it. And so looking at what we have A minus lambda I, and the determinant of it needs to be equal to 0. And so let's start just by figuring out what A minus lambda I would look like. And so looking at this function, if we were to write this as A minus lambda I, where this is our A, well, A minus lambda I is going to be 2 minus lambda, 3, 5, and 4 minus lambda. Because lambda times I is just going to be lambda on the main diagonal. Well, if we're saying that the determinant of this is equal to 0, well, the determinant of this would be 2 minus lambda times 4 minus lambda minus 3 times 5. Now we have a nice algebra 1 problem. Let's see if we can FOIL this out. We get lambda squared. 2 and 4 is going to give us a 6 lambda. And it's minus because it would be a negative 2 lambda and a negative 4 lambda. Then we have a plus 8 minus 15, which is a minus 7. This factors. And so we're going to get a lambda minus 7, lambda plus 1 equals 0. So lambda is equal to either positive 7 or lambda is equal to negative 1. Since we have two eigenvalues, we'll label them lambda 1 and lambda 2. Now that we have these eigenvalues, we can figure out what the eigenvectors are. And so in order to figure out what the eigenvectors are, remember, we're going to be using the equation A times c equals lambda times c. But we can rewrite that as A minus lambda I times c equals 0. And so we need to figure out what A minus lambda I actually is. And we have A minus lambda I up here. We just have to plug these values in. And so let's start with lambda 1 equals 7. And so when lambda 1 is equal to 7, we can plug that in for lambda here. And that is going to give us the matrix 2 minus 7 is negative 5, 3, 5, and then 4 minus 7 is a negative 3. This times, you can use whatever dummy variable you want here. I'll usually use x1, y1. Sometimes I'll use an xy or something like that. And this needs to be equal to 0, 0. So what vector is actually going to give us this? Well, looking at this, if x1 is 3 and y1 is 5, that should do it. And so c1, our first eigenvector, would be equal to 3, 5. And we can verify that. 3 times negative 5 is going to give us negative 15. 3 times 5 is going to give us a positive 15. That added together gives you 0. Same thing on the bottom. A general rule of thumb is you can just take this value here, put it on the top, this value here, put it on the bottom, and then change one of the signs. I usually try and make it the simplified version of that, whatever that simplified version might be. But that's just one of them. And so this is eigenvalue 1 and eigenvector 1. But for eigenvalue 2, which is negative 1, we do the same thing, but now we plug negative 1 in. And so 2 minus negative 1 is going to give 3. And then 5, and 4 minus negative 1 gives 5. x1, y1, 0, 0. And so what vector is going to give us 0, 0? In this case, probably the simplest one is going to be a 1, negative 1. Because 1 times 3 minus 1 times 3 gives you 0. 5 times 1, 5 times negative 1 gives 0. And so there we have it. We have 2 eigenvalues and 2 corresponding eigenvectors. For a 2x2 system, that is going to be very common. A 3x3 will often have a 3 eigenvalues and eigenvectors, but there are going to be some odd cases. For us, we're mostly going to be focusing on the more standard stuff, and so that's going to be this. But we will see real eigenvalues and we will see complex eigenvalues. For now, let's just focus on the real ones, though. Complex, We'll definitely be dealing with them by the time we get to chapter 10. If you want, in the notes, I have this problem worked out, and it looks like I did it the exact same way, which is nice. And so you start by creating the matrix A minus lambda I. Then you find the determinant of A minus lambda I, which is what we did here. And then we solve the equation, which is A minus lambda I, or the determinant of A minus lambda I equals 0. That's known as the characteristic equation. Once we've done that, we substitute each eigenvalue into the matrix, which is what we did up here. And then we set up the equation. Here it says to use x1 and x2. x1, x2 works wonderfully as well. And then find a vector x1, x2, which would make the equation true. And so in this case, 3, 5 worked great. For this one, 1, -1 works. Eigenvalues are unique for each one, but eigenvectors are not. There are an infinite number of ways we could represent an eigenvector. If we look at this first eigenvector up here, the 3, 5, we could have written that as 6, 10. It still would have been true. It still would have been an eigenvector. Any scalar multiple of an eigenvector is still going to be the same eigenvector. And so keep that in mind. An eigenvector is just an example of a vector which stays the same, or stays going in the same direction when you apply the matrix transformation. And so this is how we do it. If we want, here are some practice problems, and we can work through each one of them. And we will definitely want to do at least a few of these because they can get a little bit interesting. I do also want to point something out, though. We have a shortcut, and it is an amazing shortcut. And so the characteristic equation is the equation you set up with your eigenvalues. If you are dealing with a 2x2 system, we can actually quickly get the characteristic equation. Let me write this on the whiteboard. The characteristic equation is a way to quickly find your eigenvalues. And it is lambda squared minus the trace of the matrix times lambda plus the determinant of the matrix equals 0. This will always give you your eigenvalues. But let's work through some of these problems. And so let's start with that first one, which is 2, 5, 7, 4. And so A is equal to 2, 5, 7, 4. If we want to figure this out, we start by figuring out what A minus lambda I is. And so A minus lambda I is going to be 2 minus lambda, 5, 7, and 4 minus lambda. Once we have that, we need to take the determinant of this and set it equal to 0. That's where the characteristic equation comes in. If you take the determinant of this and set it equal to 0, it's actually just going to be this equation. It's always going to give you lambda squared minus the trace of this, which is 6 lambda, plus the determinant. The determinant in this case is going to be an 8 minus 35. Ugh, I wish I were able to do numbers quickly. Looks like a 27. Negative 27, of course. And so now we hope that this can be factored. If it can't, remember, you can always go back to the quadratic formula. And eventually we will be using the quadratic formula to solve some of these. You could also use the completing the square method. Remember, that's also a technique available to you. It's always going to be a quadratic as long as we're dealing with a 2x2 system. Once we get to 3x3s, well, you're going to have a harder time. But as long as it's 2x2, we can always just use our standard quadratic stuff. This should factor. Lambda minus 9, lambda plus 3. And so we'll get our first eigenvalue is positive 9. And our second one is negative 3. Once we have our eigenvalues, we can plug them into our equation up here and set it equal to 0. And so we are going to get 2 minus, let's do lambda 1 equals 9 first. And so 2 minus 9 is going to give us a negative 7, 5, 7. Then 4 minus 9 is going to give us a negative 5. And then this is going to be x1, x2 equals 0, 0. With this one, our eigenvector, oh, that's an ugly looking Cassie, is going to be 5, 7. And we can verify 5 times negative 7, 7 times 5. That's going to give us 0. Same in the bottom. For our second one, eigenvalue 2, our eigenvalue 2 equals negative 3. We are going to get a 2 minus negative 3 is 5. 5, 7, 7. x1, x2. And in this case, 1, negative 1 sounds pretty good. And so again, there's our eigenvalue and eigenvector, and there's our, oh, and this should be an eigenvector. Our eigenvalue and eigenvector. Let's try another one. And I think at this point, we're just going to run through a number of practice problems. It looks like I have 5 on my notes. That'll probably be enough. There are some weird things that can happen with the eigenvectors, though, and I do want to point that out. For instance, what if when you get your eigenvalue and you, I don't even care what this is, and when you plug it in, you get something like this. How about a 3, 0, and then 5, 0? In this case, what would your eigenvector be? And in this case, if we were to let our eigenvector be equal to 0, 1, then we'd be doing 0 times the first and 1 times the second, and that would certainly work. And so be aware, sometimes you'll get terms that look like this. There are a few other weird cases. I don't know how weird the examples are going to get here in the homework, but hopefully not too bad. And so let's do the next one, which is the matrix A is equal to 1, negative 3, 7, or sorry, negative 7, and 5. Again, we can figure out what A minus lambda I is equal to. A minus lambda I is going to be 1 minus lambda, negative 3, negative 7, and 5 minus lambda. We can then use our characteristic equation. And so it's going to be lambda squared minus the trace. And so that's going to be minus 6 lambda. And then it's going to be plus the determinant. So the determinant in this case is going to be 5 minus 21. It's going to be a negative 16. Factor. Set each factor equal to 0. And then we can find our eigenvectors. Eventually, this just becomes routine, which is good. You want it to be routine, makes it a little easier. And so for lambda 1 equals 8, we are going to have 1 minus 8 is -7. And then 5 minus 8 is going to be a -3. So our, that is an ugly eigenvector. Drawing ugly eigenvectors is a specialty of mine. There we go. So our first eigenvector, well, looking at this, the -7 and -3, if we were to make this a 3 and a -7, that should do it. Give us a -21 and a +21. For our second eigenvector, we plug in the -2. 1 minus -2 is going to give a 3. -3, then a -7 and a +7. Then we have x1, x2. And so our second eigenvector is going to be 1, 1. And so eigenvalue, eigenvector, eigenvalue, eigenvector. Let's try another. If you want to really practice, you can really choose any 4 numbers and see if you can find the eigenvalues and eigenvectors of them. You'll quickly notice that most of them are going to require the quadratic formula, but that's okay. 4, 0, 5, -4. And so with this one, same process. And so it's going to be a minus lambda I is going to be equal to 4 minus lambda, 0, 5, and then -4 minus lambda. My hunch is that the main diagonal values are going to give us our eigenvalues. And so it'll be 4 and -4. But let's verify that real quick. And so looking at this, our characteristic equation is lambda squared minus the trace. So 4 plus -4 is just 0 lambda. And so then it's going to be plus our determinant, which is -16. And so sure enough, our eigenvalues are going to be 4 and -4. If we let our lambda 1 be 4, so our first eigenvalue is 4, then we end up with 4 minus 4 is 0, 0, 5, and then the bottom one, -4 minus 4 is -8. And then x1, x2. So notice in this case, we have 0, 0 on the top. Do not set your eigenvector equal to 0, 0. It doesn't have a direction. And so instead use this bottom row. And so with this bottom row, our eigenvector 1 would be 8, 5. Remember, this vector needs to work for both. It's guaranteed to work on the top because no matter what you plug into the top, you're getting 0. And in the bottom, you get 40 minus 40. For eigenvector 2, which is -4, well, now we're going to get 8, 0, 5, 0. And so that tells us that our eigenvector is going to be 0, 1. Because 0 times the first row plus 1 times the second row is definitely going to do it for us. We have one more, and then we'll try a 3 by 3. So this next one's another kind of special case. So 3, -3, then -7, 7. What's special about this one is one of the eigenvalues is going to be 0. But let's see how that works. We're dealing with lambda squared, or I guess we'll start by writing out the matrix A minus lambda I. It's going to be 3 minus lambda, -3, -7, and 7 minus lambda. And so now we're going to have our characteristic equation is lambda squared minus the trace. And so 3 and 7 is 10. And then the determinant. The determinant of this, though, is 0. Factoring this, we get lambda times lambda minus 10 equals 0. So our lambda 1 is 0, and lambda 2 is 10. Now that we have those, we can figure out what our eigenvectors are. And so our eigenvectors for lambda 1 equals 0, well, our matrix is just going to stay the same. 3, -3, -7, 7. And in this case, our eigenvector is just going to be 1, 1. For lambda 2, which is 10, same idea. And so now it's going to be 3 minus 10 is -7, -3, -7, then a -3. And so looking at this, our second eigenvector is going to be a, how about a 3, -7? It's 3 times the first, 7 times the second, swap one of the sides, and you are good to go. And so that's pretty much all the different things that you'll see for 2 by 2s for now. As mentioned, there are a lot of weird things that can happen. You could get repeated eigenvalues, in which case you can have 2 distinct eigenvectors, but they can be a little trickier to find. You could also get complex eigenvalues, in which case you will have some weird things to do with your eigenvectors, but we'll save that for chapter 10. And there's a lot of weird little cases, like when eigenvalues are equal to 0, you can get some very odd behavior out of them. For now, though, we're going to keep it relatively painless, except for this one. So let's do a 3 by 3. So we will do 1, 0, or sorry, the one I have in the notes is 1, 2, 1, 0, 3, 0, 1, 0, 1. Now, the nice formula that we had involving the trace and the determinant no longer applies. Because remember, that only works for a 2 by 2 system. If we're dealing with a 3 by 3 system, we have to go back and remember that we're solving the determinant of A minus lambda I equals 0. This equation works no matter the dimension, but the determinant in higher dimensions can get messier. And so let's see if we can figure this one out and see if it fits on our whiteboard. And so we begin by doing A minus lambda I. And so A minus lambda I is going to be a 1 minus lambda, 2, 1, a 0, a 3 minus lambda, 0, and then a 1, a 0, and a 1 minus lambda. Now, if you remember, to find the determinant of a 3 by 3, there are multiple ways. Perhaps the easiest would be to repeat the first two columns, though. So it'll be a 1 minus lambda and a 2, a 0 and a 3 minus lambda, a 1 and a 0. And I'm just double checking that I've copied everything down correctly up to this point. If you make a small mistake on one of these problems, it can really just destroy the problem. And so you want to make sure you are being meticulous when you are doing these. And so now we can go down the main diagonals and the anti-diagonals. So remember, going down the main diagonals, we would say 1 minus lambda, 3 minus lambda, 1 minus lambda. 2 times 0 times 1 is 0. 1 times 0 times 0 is 0. So now going down the anti-diagonals, we get 1 times 1 times 3 minus lambda. We get 0, and we get 0. And so we have to set this equal to 0 and solve. We can factor a little bit. Let's see what we can do here. And so if we factor the 3 minus lambda out, and so 3 minus lambda, we're going to be left with 1 minus lambda times 1 minus lambda, which is 1 minus 2 lambda plus lambda squared, minus 1, because we had one of these that we factored out. The ones would cancel out, meaning we could factor a lambda out of this, giving us a 3 minus lambda, a lambda, and then a lambda minus 2. So we have three eigenvalues. Lambda 1 equals 0. Lambda 2 equals 3. Lambda 3, I'm going to swap these just to make it a little bit more or easier to recognize. Lambda 2 equals 2, and lambda 3 equals 3. Because at 2, we get 0, at 3, we get 0, and at 0, we get 0. So now comes the tricky part. We have to find the eigenvectors for this 3 by 3 system. And so for lambda 1 equal to 0, I'm just going to get rid of this bit here so that we can see our matrix again. We are going to have this equation. And so it is going to be 1 minus 0, which is just 1, 2, 1, 0, 3, 0, and then a 1, and then a 0, 1. x1, x2, x3 equals 0, 0, 0. In this case, our eigenvector 1, while looking at this, we would need to somehow get some combination of these. And it can be a little tricky. Really, the top one's going to be the interesting one. If we let the middle value be 0, and then we do a 1, negative 1, that should do it. The way that I got that was kind of looking at what patterns were emerging from this. And I noticed that I had this 1, 1, and this 1, 1. If I got rid of the central column, then the 1, 1, 1, 1, that's definitely going to be dependent upon one another. If we could do a 1, negative 1 on that, then we would get that it goes to 0. And so this is our first eigenvector. See if I can write a little smaller for the next couple. For eigenvalue 2, which is 2, we are going to have 1 minus 2 is negative 1, 2, 1. 0. 3 minus 2 is going to be a 1. Then this is going to go to 0, 1, 0, and 1 minus 2 is -1. And I think we can do something similar. And so following that same pattern, if we let C2 be equal to 1, 0, 1, we'll note this gets rid of the middle column. Then we're going to have the 1 and 1. They are going to cancel each other out. And so, yeah, that should work. For our third one, lambda 3 equals 3. Let's see. So we are going to have a 1 minus 3. Let me verify that. Yes. And so 1 minus 3 is -2. Then we're going to have 2, 1, 0, 0, 0. That's convenient. And 1, 0, and 3 minus 2 is going to be, what is that? Or sorry, 1 minus 3 is going to be -2. x1, x2, x3. Well, this one's a little bit messier, but the fact that we have an entire row equal to 0 means we have a little bit of playroom. I would probably start by looking at this bottom one. If we let this be 0, the 1 and the -2, then that would give us our eigenvector as being, let's say, a 2, a something, and a 1. Because 2 times 1 and -2 times 1 gives us 0. But now when we look up at this top one, we're looking at the top row and these two values. It's -2 times 2 plus 2 times something plus 1 times 1 equals 0. And we need to figure out what this something is. And that's just an algebra problem. That's going to give us a 1, which we can move over and get a -1, or we could even combine with this. 1 and -4 is going to be a -3. So 2x equals 3, x equals 3/2. If we wanted to write it without a fraction, we could multiply everything by 2, giving us 4, 3, 2. Fancy. And so that's a 3x3 system. And so we had a 3x3 matrix. We were able to find the 3 eigenvalues. And then figuring out the eigenvectors, it took a little bit more logic than most of the 2x2s. The 2x2s in general, they were pretty obvious. But the 3x3s, they can get a little bit more complex. And you really got to think about how we can make it so that when we multiply by the vector, we're going to get 0, 0, 0 in such a way where the vector itself is not always 0. Remember, eigenvectors should never be 0, ever. When we multiply by the matrix, that's when we should get the 0. Let's share the screen just to kind of wrap it up. And so there are the 5 problems that we just did. I do want to show something like this, though, because this is something that is going to be coming very quickly. And this is what Chapter 10 is all about. Chapter 10 is all about trying to understand systems of differential equations using eigenvectors and eigenvalues. This is an example of a system which has a complex eigenvalues and eigenvectors in the center, and then it has 2 saddle ones where you have a positive and negative on either side of it. What this is really representing, though, is an equation like this. And so let's say that we have two variables, x and y. So x of t and y of t. Well, if we were to do x prime of t, and we knew that x prime was equal to some combination of ax, or of x and y, so ax plus by, and y prime is equal to cx plus dy, we can write this in matrix notation. In matrix notation, this would be x dot, well, usually we use the dot notation when we're talking about vectors like this, is equal to A, where A is equal to the matrix A, B, C, D, and X is equal to X, Y. X dot is equal to A times X, where X is a vector and A is that matrix. It turns out the solution to this is going to be tied to the eigenvalues and eigenvectors of this matrix. And the eigenvalues are going to determine what the behavior is of this vector field. And so if we have two systems, a system with two equations, and they're both differential equations, we can actually solve this using our eigenvalues and eigenvectors. What's interesting is depending on the eigenvalues, we get a lot of different behavior. And that's what this chart is trying to show. Let's see if I can zoom in on it or not. There we go. And so depending on the types of eigenvalues and eigenvectors you have, you're going to have different behavior. This on top, you can see one is positive and one is negative. If one is positive and one is negative, then we're going to get a saddle, where things are coming towards the center and then they're running away as quickly as they can. If you have both of them are positive, then everything is going to be unstable and it's going to be running away from your central points. If everything is negative, then it's going to be going towards the central points. If you have complex values, that's on this bottom part, you're going to have things spiraling or circling the central point. When we're talking about nonlinear dynamics, though, you could have multiple of these in the same system. And so when you start thinking about things like the predator-prey model, or SIR models, epidemic models, or if you're modeling tumor growth in 3 dimensions, you're dealing with systems that look something like this. And trying to understand the long-term behavior really boils down to understanding what the eigenvalues are. And so that's where this is coming in. We're not going to get into that until chapter 10, but the entirety of chapter 10 is going to be about using eigenvalues and eigenvectors to understand systems of differential equations. That said, that brings us to the end of today's lesson. Today, we focused exclusively on eigenvalues and eigenvectors to finish off our chapter on matrices, which was chapter 8. You have a tremendous amount of homework ahead of you, so I will let you get to it. Take care of yourselves.